Hi everybody, welcome to another video in differential equations, section 2.5, special integrating factors. So this will not be a very long section. What we study is that for some equation that it is not exact, but where we multiply by something, the equation becomes exact. So originally, the equation is not exact, but the equation is exact by multiplying mute of x1 on both sides. So it is exact with the integrating factor. Right. So the application will be kind of limited because some certain thing has to happen for the not exact equation to be exact. Right. So that special condition is this: if we have my minus nx divided by n is continuous and only depends on x, then this is the integrating factor. If this is continuous and only depends on y, then we have that is the integrating factor. So kind of strictly this condition, this function has to depend only on x. So that's why the mu is only depends on x. Or it can be this if it only depends on y. So pretty straightforward, this section, either that or that. Of course, like I said, kind of limited. Some certain things have to be perfect for this condition to work. Right, let's look at some examples. We solve this equation: 2x squared plus y times dx plus x squared y minus x dy. Usually the equation given in this form, we suspect that it is exact because we have m dx and n dy. So we test to see if it is exact. M is that, so derivative with respect to y is 1. N is x squared y minus x, derivative with respect to x is this. They are not the same. Since my not equal to nx, the equation is not exact because they're not equal. Right. Now, if it is not exact, then we'll try either one of this. If it only depends on x or only depends on y, then we have something. We have the integrating factor which we can use. So note that in this case we had m of y and n of x divided by n, and we end up with this, which is -2 x to -1, and it only depends on x. So if my minus nx over n only depend on x, then the integrating factor is this, and we have x to -2, right? So the math here is not that bad. Now we multiply both sides by the integrating factor. When we do that, and we'll test m sub y and n sub x, the equation becomes exact. So originally the equation is not exact, but when we multiply both sides by this integrating factor, the equation becomes exact. Now if equation is exact, then we know how to do it. Integrate, differentiate with respect to x, with respect to y. Right. So of course, continue that, we have a solution here. Right. So I just want to make a little note here. So pretty simple, right? Original equation not exact, then try one of this. If it's true that it only depends on x for that and only depends on y for that, then we have the integrating factor. Multiply both sides, the equation is exact. So certainly we know how to solve the exact equation, right? Now, just make a little note here on this special problem. Right. So originally this is the equation. So I will write this. Originally the equation to x squared y dx x squared y minus x dy. Right, so this is the original equation. Now we multiply by the integrating factor of negative 2x to negative 1. Right, so special. I will explain why do we have this, but when we look at this, note that if x equal to 0, then dx is equal to 0. For this equation, x equal to 0 is a solution. We can check real quick. If x equal to 0, then dx is equal to 0, so that is 0. If x equal to 0, this equal to 0, right? So x equal to 0 implies dx equal to 0 as well. Now dx equal to 0, this equal to 0, x equal to 0, those two equal to 0, so 0 equal to 0. So x equal to 0 is a solution. So that is, before we do anything, we know the solution is x equal to 0 is one of those solutions. Now, after we multiply by the integrating factor, so originally that's what we have. So after multiplying integrating factor, this is mu of x. What equation do we have? When we multiply by the integrating factor, we have this equation. So this equation, clearly x cannot be equal to 0. If x equal to 0, x to negative 2 is undefined, right? Because x to the negative 2 is equal to 1 over x squared. And if you put x equal to 0 there, it is undefined. So therefore, this equation, x equal to 0, is not a solution. So what do we conclude about this? So originally x equal to 0 is a solution. After multiplying into it, it is not a solution anymore. So the conclusion here is we lost a solution of x equal to 0. So the note here, the solution x equal to 0 is lost. After we multiply the integrating factor, then you ask, why do we have why x equal to 0 so special here? Why we focus on that? Right? Simply because the integrating factor is due to the negative 2x to negative 1 or negative 2 over x. So x equal to 0 have the special meaning to it. It could make the function undefined. Right. So when we solve the equation this way, just need to check for that. Right, and now let's look at the second example here. So first thing is, we check to see if it is exact. If it's not exact, try to see if we can make it exact. First, check for exactness. So I will let m equal to 2xy and n equal to y squared minus 3x squared. Right, and check for exact equation. We will derivative of m with respect to y and derivative of n with respect to x. M with respect to y is 2x. And n with respect to x is negative 6x. And they are not the same. So because they are not equal, so it's not exact. Right, next. Can we make that exact? Right. So in order to do that, we will check these two conditions. Either my minus nx over n or nx minus my over n over m. So either, by the way I remember this, if we start with m, so the n when we divide is always the same thing. And then when we write this, it only depends on x. So like nx and nx, my and my, this only depends on y. Right. So if we start with n, we divide by m and it will depend on y. So I will write like this. If we start with n, it will be nx minus my over m, and it depends on y only. And if I start with m, it will be my minus nx and divide by the second, and it depends on the second. So it depends on x only. Right. And we just integrate, a to integral of that will be the integrating factor. Right. So surely if we subtract them, we only have x, right? Whether my minus nx or nx minus my only depend on x. But which one do we divide by? Do we divide by this or we divide by this? One thing for sure, if we subtract those two, doesn't matter the order. If we divide by m, the x and x cancel out, so it only depends on y. So that means it only depends on y, so we're going to use this. So here, note, this is what we do. Again, if we start with n, and n sub x minus m sub y over m. If we do that, and it only depends on y, then that we have an integrating factor. So nx is negative 6x. my over m negative 8x to xy, x and x cancel out, and negative 8 and negative 4. So negative 8 and 2 cancel out is negative 4. So we have negative 4 over y. Or we can say negative 4 y to negative y. This only depends on y. It only depends on y. So we would have the integrating factor of that. Negative 4 y to -1. Right, so that gives us a -4 integral of ln of y. Integral of y to -1 is ln of absolute value of y. I'll take the -4 inside and I will rewrite this as e to ln of absolute value of y to -4, and in ln cancel out. So this is kind of like linear equation, linear first order equation. Right, so for this, it only depends on y. I mean, for that, then we have integration factor, of course, only have y in it. That's why we only need y here. And so, again, so that is 1 over y absolute value 4th power. And again, this is even power, so it's going to be even. Besides, integration factor, remember section 2.3, if there's absolute values, we can throw that away, because that's, we multiply both sides by the nature of integrating factor. We don't really need absolute values, because if it is the plus or minus, multiply both sides, that cancel out. So that's just 1 over y to the 4th, or y to -4, either way. Right, multiply both sides by that. That's spelled correctly. Right. Right, multiply both sides by the integrating factor. So the equation so that becomes 2x y to -3 dx multiply inside y to -2 minus 3 x squared y to -4. Right. Now we have a new equation. Now we will check to see if this is exact. So we just checked. So m equal to 2x y to -3, and n is y to -2 minus 3 x squared y to -4. Take derivative of m with respect to y. Give us -6 x y to -4, and derivative of this with respect to x give us -6x y to -4, and they are the same. So this new equation is exact. Right. So if it is exact, then we solve that like the exact equation on the previous section. So the next step is, because it is exact, we can say there exists a function f of xy such that partial derivative with respect to x is equal to m, and partial derivative respect to y equal to n, which is this. And so integrate and differentiate. So exact equation similar to previous section. So 1. I will integrate this with respect to x. With respect to x. So if f of x derivative with respect to x is that to get back to the function. Integrate to x, y to negative 3 respect to x. Y negative 3, y to negative 3 is a constant. We just integrate to x. Integrate to x is to x squared. It's x squared, I mean. And then we have a constant. Since this is with respect to x, the constant may have y in it. So 2 and 2 cancel out. We have x squared y to negative 3 plus g y of y. So the first step is integrate with respect to x. The second step, of course, differentiate the result with respect to y. So that one derivative with respect to y. So we have x squared. Derivative with respect to y is negative 3. Y is negative 2. I mean negative 4, right? Yeah. So that is derivative of y with respect to y plus g prime of y. And this will be made equal to n. So this is derivative with respect to y is equal to n. Derivative with respect to x is equal to n. Right. Now we will rewrite this negative 3 x squared y to negative 4 plus g prime of y, and n is equal to this. Right. And usually if we do this correctly, there should be something to cancel on both sides, and we do. So g prime of y is equal to y to negative 2. Now we just need to integrate this and to have g of y. So g of y is equal to integral of y to negative 2 dy. And that gives us y increase the power by negative 1 and over negative 1 plus c. All we can say is equal to negative y to negative 1 plus c. And we substitute that into g of y here. I substitute that in there. So we have f of xy equal to x squared y to negative 3 minus y to negative 1 plus c or we write x squared y to negative 3 minus y to negative 1 equal to c. So it's a solution. So we write solution in an equation implicit form. So that is the solution. Of course, we can check with the original equation. That certainly works. Right, and that certainly works with this equation as well. Right, now, how about the solution losing, or do we lose any solution, or we gain any solution? So from the beginning, this equation, by the way, this one we have y, integrating factor is y to the negative 4, so y equal to 0 is a significant, because y equal to 0 make this one undefined. So let's look for this equation. If y equal to 0, that equal to 0. If y equal to 0, dy is equal to 0, so the whole thing is equal to 0. So for this equation, y equal to 0 is a solution. So originally we have a solution of y equal to 0. But after we multiply it, we look at this equation. Because of this, and even this, y cannot equal to 0. So y equal to 0 is not a solution. So when we look at the integrating factor, it has the significant y to negative 4, and it cannot be equal to 0. So then we see, do we gain or do we lose any solution? So here we have y equal to 0. Originally is a solution, but after that it is not a solution anymore. So we have something before, and then we don't have it anymore, which means we lost a solution. So in this case, y equal to 0, the solution y equal to 0 is lost. So or I just say solution y equal to 0 is lost. Right. So yeah, I'm not worried about x equal to 0, right? If x equal to 0, it is not a solution originally or after that. The reason we choose y equal to 0 because of the integrating factor. It depends on y only. In this particular, y could be equal to 0 is a significant, so we have to worry about that. But other than that, equation not exact, we make it exact and we solve for that. So that should not be that difficult. The application though kind of limited because a lot of things have to work out perfectly for this method to work. Right, let's look at this solution and discuss the loss and gain of solution. So we do the same thing. First, is it exact? And the answer most likely is no, right? Because in this case we have to do something to make it exact. M equal to 2x and n is that. So we'll take the derivative of m with respect to y and n with respect to x. With respect to x, we just do x and then y to negative 1. Right, simple enough. And they are not the same, so it is not exact. So it is not exact. I just spell it out. That would be better than just write any simple. Right. The second, can we make it exact? Right. So we subtract them in any order. We have 2x and y to negative 1, right? But if we divide by 2x, the x and the x cancel out. We only have y to negative 1, so that's perfect. So if we divide, so the way we think about this, if we divide by m, then it only depends on y. So again, if we divide by m, it only depends on y, so that is perfect. So we'll note that if we start with n and we have nx minus my, since we divide by my, we divide by m, and whatever it is, it should only depend on y. So n sub x, that minus m of y, 0 divided by m 2x. So I have 2xy to negative 1 over 2x equal to y to negative 1. Right. So it only depends on y. By the way, if you happen to switch those two, we have opposite to this. But that still depends on y. But just make sure that it is in the right form. So this only depends on y. So the integrating factor will be the function of y only. And this example is I choose to be relatively simple. Y to negative 1, that is ln, and cancel out a and ln, so that's just y, absolute values. And once again, the nature of integrating factor, we can just ignore the absolute values. Because we multiply both sides with plus or minus doesn't affect the problem. Right. Now multiply both sides by that and see if it is exact. It should be exact, because it only depends on y. So multiply by y on both sides. 2x dx multiply by y and then plus y multiply that gives us 2xy dx multiplied inside we have y squared plus x squared, y and y to negative 1 cancel out. Right, now I will check for exactness again. Let m equal to 2xy. So the derivative of m with respect to y is 2x. Now let n x squared plus y squared or y squared plus x squared. The derivative with respect to x is also 2x. Now these two are the same. So the equation is exact. Now if it is exact, then we can solve for it. So if it is exact, we can say there exists a potential function there exists f of xy such that derivative with respect to x is equal to m. By the way, in the next section, we'll solve this kind of equation. I mean, this particular equation differently. There's another way to do that. But for now, let's just solve the exact equation. It's actually easier. It's more elegant too. Y squared plus x squared. When we solve the exact equation, the margin for error, the room for error, usually relatively small because it's kind of checked out perfectly. You will see. First, we can pick one of them and integrate, and then differentiate, and then match with the other. Let's use this one. Integrate. With respect to x, and then we differentiate whatever we have with respect to y and match with n. Right, so f of xy integral to xy dx, because that with respect to x, right? So integral of 2xy, so that's easy. That gives us 2x squared over 2 times y plus g of y. 2 and 2 cancel out, so f of xy equal to x squared y plus g of y. So integrate that. And then we will differentiate with respect to y. Differentiate what we have with respect to y. With respect to y, derivative of x squared y, derivative of y is 1. So f x squared times 1 plus derivative of y. And we will make it equal to n. Right, rewrite this. X squared plus g prime of y equal to y squared plus x squared. Usually if everything works out, there will be something cancel out. So we just integrate this. So g prime of y is equal to y squared. So integrate that, give us g of y equal to integral of y squared dy, which is y cubed over 3 plus the constant c. So we substitute this into g of y. So we have f of xy equal to x squared y plus y cubed over 3 plus c. Or we can write x squared y plus, I can write y over 3 y cubed equal to c. So the solution we should write as an implicit equation because there's no function f of xy. We don't want to introduce some other function in terms of xy like that. But this is the solution. So right, next, discuss the loss and gain of solutions. Right, so what special that we have to worry about here? Now, the integrating factor is y. So that's the significance is y equal to 0. Right? If we have y to negative something, that also the significant. So now we see if y equal to 0 is a solution or not. Right, number 4. I'll just do before and after. Before and after multiplying the integrating factor. Before, what do we have? Original problem. I just copy from the original problem. 2x dx plus y plus x squared y to negative 1 dy equal to 0. That is before. And after we have 2xy, I mean this is the equation after we multiply the integrating factor. That is before. It is after. 2xy dx plus y squared plus x squared dy. And the particular solution that we worry about is something that has y in it. So y equal to 0. So it's y equal to 0 is a solution. Now first, before we have this term out of the window, y cannot equal to 0 because y equal to 0, that one is undefined. So we not even think about that. So originally or before y equal to 0 is not a solution. And after we multiply by the integrating factor y equal to 0, if y equal to 0, this one equal to 0. Y equal to 0, dy is equal to 0 as well. So all of this equal to 0. So originally y is not a solution, but after that y can be equal to 0. Right, and then the last part of it is just common sense. If we didn't have something before and we have something after, so that means we gain a solution, right? So we did originally it is not a solution, but it is a solution after multiplying the integrating factor. So we gain a solution of y equal to 0. Right, I've run out of space, but that one obvious, right? We didn't have before and we have it after, that means we gain a solution. Right, and by the way, we could have a case where originally it's not a solution and after that it is not a solution. So if we don't have anything before and we don't have anything after, we neither gain or lost anything. That could be the case as well. Right, or we might have a solution before and we have a solution after. That could be the case as well. So in this case, usually when we look at the integrating factor that is have some special, is that equal to 0 could be a solution before, could be a solution after, and then in that case we might gain or lose a solution. Anyway, with that I stop section 2.5 here. As always, thank you for watching. See you in another video in differential equations.